Thank you. Thanks for the introduction, and thanks for having me here. So it seems like I'm starting off the distributed session, and this talk is indeed on distributed optimization. So I'll talk about submodular maximization, and the setup that we're interested here is that the data is very large and it's distributed across machines, and we're interested in seeing what we can do. So this talk is based on joint work with my amazing collaborators. So Raphael is my student, who is here, and Justin. And I should say all of the credit for the slides go to Justin, so I stole them from him, but all of the mistakes are mine. I made some changes. So the viewpoint that we take here is that of combinatorial optimization. So we are interested in fairly general optimization problems. So perhaps a familiar setup that you've seen over and over is that we have some collection of objects, and we have some function on subsets of these objects. And we also have some feasibility constraints. So some subsets of these elements are feasible and some are not. And our goal is to find a feasible subset that maximizes our function f. So you can think of this as an objective function. And generally, we want to keep this framework as abstract or as general as possible by not imposing too many constraints on the function or the feasibility set. And the reason for this is perhaps obvious. So we want to capture as many problems of interest as possible. But of course, there is a computing goal here that we also want to be able to efficiently optimize these problems, so we want very efficient algorithms. So these two goals are conflicting, so in general we need to place some restrictions on the function and the feasibility set. And a very nice restriction that we can impose, which is still very general, is the notion of submodularity, which we've already seen in Amit's talk in a different context. Just to remind you, so here submodularity will be a property of our objective function f. So our function f is a set function over our ground set. And we're going to say it's submodular if it satisfies this inequality on the slide for any two sets. So the value of the function on A together with the value of the function on B, it needs to be at least the value on the intersection together with the value on the union. And throughout this talk, I'll assume that the functions we're working with are both submodular and monotone until perhaps the very end. So if throughout, think of the function being monotone, which means that if I look at a superset, my value should only increase. So perhaps a more intuitive definition that you can think about, which I like more, is that of diminishing returns, which is completely equivalent. So submodularity captures diminishing returns in the following sense. So if we have two sets A and B, one of which is the subset of the other, so let's say A is a subset of B, and we consider adding some element x, then the marginal gain that we get, it should be larger if we add it to A as opposed to B. Okay, so these two definitions are completely equivalent, but I find the second one easier to think about. Good. So modularity is a very nice restriction because, as we'll see, it comes with some significant algorithmic benefits, but it's also very general. So it generalizes linear functions, so it captures the classical combinatorial optimization problems, but it also captures a lot of other functions that are not linear, but they tend to arise a lot in practice. So one that we'll see in this talk is the coverage function. So we have a collection of sets, and the coverage, the value of a subset is simply the number of elements covered. So another one is the entropy of a set of random variables. So we have a collection of random variables in a joint distribution. If we're also working with graphs, either direct or undirected, the capacity of a cut is a submodular function. So if you look at any set, this is the weight of the edges leaving. And several other very nice functions are submodular. So this is one of the reasons why submodular functions have found many applications in machine learning, computer vision, economics, and many other settings. So So instead of being a bit vague about submodularity, let me give you two concrete examples to think about. And you can think about them as concrete things throughout the talk if you want. What we'll end up doing is fairly general, but it's good to have some concrete examples. So one of them uses the coverage function. So let's think about the following somewhat toyish setting. So we have some sensors that we want to place, and we have some possible locations for them. And these sensors have different modes, so they can be set in different modes. And each different mode will give us a different coverage profile for the sensors. And we want to find the locations where to place these sensors. And we also want to set the modes of the sensors so that we get as much coverage as possible. So concretely, imagine that our sensors look like this. So here's a sensor with all of the possible modes. And these ellipses are the different areas that a given mode will cover. So each ellipse is a mode of the sensor. So we might want to place this blue sensor at some location. So let's say we place another and a third one. And for each of these, we'll select some mode, so perhaps these ones. And the total coverage that we get is the total area. So you can see there's some overlap between these sensors. That's where the submodularity comes from. OK? So if you put the combinatorial optimization cap, what kind of problem is this? So perhaps in the most general terms, this is a submodular maximization problem. And as we'll see in a moment, is a matrix constrained maximization problem. So if you think about it, so one way to define the problem is to say, I have some coverage function on these ellipses corresponding to the different modes of the different sensors. And I want to pick a subset of them. But I'm restricted in the following way. So I'm only allowed to pick a single ellipse for each sensor. So we can only operate in a single mode. So we have a constraint that among all of the ellipses of a given sensor, we can only pick one. And that's just a partition matrix. So this is a submodular maximization with a partition matrix constraint. Okay. So another example that I like to mention is that of identifying representative items in a very large data set. And concretely, let's think about finding representative images in a huge data set, such as the tiny images. So the subset of the tiny images look like this. So each of those little things is a tiny image. And we want to pick a subset of them, a very small subset of them, such as these ones. So out of 80 million tiny images, and maybe I want to pick 100. Okay? Yes?
What's the criteria?
Yes. So I'll mention in a moment. OK, so what does this mean? So one way to model this, which I've learned from machine learning people, is the following. So it's a little bit technical. So how do we model this? So I'll model it as a submodular maximization with a cardinality constraint. So we want to pick at most k images where you can think of k as being very small. But what is the objective? Exactly as Piotr was mentioning. So here we'll think of this huge set of images as a huge set of vectors. So each image will be a vector in very high dimensions. And we also think about the setting where we have some information about these images. So in particular, we know how different they are. So we have some function that tells us, given two images, how different are they? OK? And we want to pick k of these images and to minimize a certain loss function. This loss function is a normalized k-median objective. So if S is the set of images that I've picked, then the total loss is proportional to the sum of the distances from each image in the entire data set to its closest, in terms of this difference, image in the set that I've picked. And we'll normalize this by the number of total image in the entire data set so that the loss is between 0 and 1. Okay, so it's just a normalized k-median. Okay, so this objective is actually supermodular, and we're interested in minimizing it. So what we can do to make it a submodular maximization is that we can flip it. So the way we do this is by picking a single distinguished vector. So let's say E0. So this could be the O0 vector. And define a function f to be the loss of this single vector minus the loss of adding this single vector to an entire set S. Okay. So since we're taking the negative of a supermodular function, then we get a submodular function. Yes?
So if you're approximating f, it won't approximate.
Yes. So the normalization helps in that way.
Oh.
The original problem is the k-median.
Yeah, the original problem is the k-median problem. Whether approximating f really is meaningful for this application remains to, it depends, but this is one model. This is one way machine learning people have solved this clustering problem. Okay. Any other questions? Okay. Okay. So these are the two examples that we'll see, at least in the experiments towards the end. Okay. So as I mentioned at the very beginning, sort of the focus in this talk is more on the setting where this entire data set over which we want to optimize is huge. So for example, tiny images has 80 million images, and we have pairwise differences between them. So storing all of this data on a single machine is not feasible for us. So we're going to assume that our data set is so large that it cannot fit on a single machine. And the goal is to solve these problems in a MapReduce style. So we want to sort of partition the data and do something on a very small chunk of the data. Okay. And just to recap the problem, just so that I remind you of my notation. So in this talk, we'll be interested in maximizing a submodular function. And we'll do that subject to a hereditary constraint. So that means that if I have a set that is feasible, then all of its subsets are feasible. So you can think about a cardinality constraint or a matrix rank constraint, or a matrix constraint of some rank. And we want to find a feasible subset that maximizes this function. So throughout this talk, n is going to be the total number of elements in the data set. And k would be the maximum size of a feasible solution. And m is going to be the number of machines. So I'll assume that we're working in a setting where we have m machines. Okay. So before we actually get to how we solve submodular maximization in a distributed setting, let's review some classical results. Namely, how do you solve these problems in the sequential setting? Okay. So submodular maximization is fairly general, but luckily there's a very nice algorithm that solves this problem pretty well, at least for some types of constraints. And this is perhaps the classical greedy algorithm, which perhaps most of you might know already. So basically, the idea is very simple. So we'll start with with the empty solution, and we'll just pick some elements. And the way we do so is greedily. So while there exist some elements that we can still add without violating feasibility, we'll pick one of them that give us the maximal marginal gain on top of the current solution that we already have. And we'll do this until we can't add any elements anymore, and we just return that set. Okay? This algorithm is very nice because for several reasons. One is very easy to implement. So this is the kind of an algorithm that practitioners like all the time. So greedy algorithms are very powerful in that way. And in this particular case, submodularity actually gives us some very strong theoretical guarantees. So the classical work of Nimhauser, Wolfsky, and Fisher tells us that this algorithm actually comes with some surprising approximation guarantees. So we get 1 minus 1 over e for a cardinality constraint. And this is actually tight. And in fact, even for a matrix constraint, we get a half approximation. So one of the main downsides of this algorithm is that of course, it's very sequential and centralized. And its running time is a bit high. It's n times k because in every iteration, we actually need to recompute all of the marginal values to find the best element. So we could speed this up, but this will not save us in the setting where we can't even do linear time. Okay, so what we do when the data is very large. Okay, so here's a very nice, very natural idea that comes from the work of Mirza Soleiman et al. From NIPS 2 years ago. So here's a very nice idea that they had to make this greedy algorithm into a distributed one. So what they say is the following. So let's take our data set, so the tiny images or whatever, and we'll distribute them to our machines. So we're going to evenly partition them onto the machines. And on each of the machines, let's just run the greedy algorithm and pick k elements from the images on each of the machines. Okay? So now we'll take, in the second round, we'll take all of these greedy solutions and just put them on a single machine. And we run greedy again and pick our final set of k elements. Okay? And output that. Okay? So this was their distributed greedy algorithm. And it's quite nice. It's embarrassingly parallel. It only requires 2 rounds of communication. And it's very natural. It's the kind of algorithm a practitioner might want to use. But the major downside is that the approximation ratio that they could guarantee actually scales rather poorly with the number of machines. So it's about 1/m, where m is the number of machines. And in fact, they showed that even if we were to use the optimal algorithm on each of the machines and solve the problem exactly, which we cannot, but let's say we could, then this would still not save us from the 1/m behavior. Okay. So it seems that, at least in the setting, we're more or less stuck with 1/m. But it turns out that this is not quite the case. In fact, one can show a slight improvement over this. So it actually turns out that running the optimal algorithm on each of the machines is not a good idea. In fact, using greedy is better if one cares about worst case performance, because at least that gives us 1/√m approximation. And the reason for this is that the problem doesn't quite have optimal substructures. So it's not necessarily helpful to do the optimal thing. Okay, so we can construct some bad examples for algorithms of this form where we run greedy or even the optimal algorithms on each of the machines. And in fact, we can provably show that we cannot get away with very good approximation, at least if the data is distributed adversarially in the first round. So there's some nice lower bounds coming from core sets from the work of Piotr and others. And I think Vahab will talk about them, so I'll just let him.
I'll mention them.
Okay. So these kind of lower bounds tells us that we can't do very well even if we allow other types of algorithms. Okay. But if we look at the work of Mirza Soleiman et al., we notice that they showed in very extensive experiments that these algorithms work quite well. So where they could actually run the sequential greedy algorithm, they compared the distributed algorithm with the sequential one. And they actually noticed that they're very close. So this algorithm doesn't seem to be losing that much, at least not on real instances. So it's kind of intriguing to see why that is. So we looked at this algorithm very closely, and one thing that we noticed is that one thing that they were doing, which they were not using in the analysis, but it was definitely used in the experiments, was randomness. So they actually, in the experiments, they were running a randomized distributed greedy, which was exactly as before, except that instead of arbitrarily partitioning the elements onto the machines in the first round. They were randomly distributing them. Okay, so each element went to a machine chosen uniformly at random. And otherwise, the algorithm was exactly the same. And perhaps surprisingly, what we could show is that this simple modification is actually crucial. And in fact, for this variant, where things are randomly distributed, we can prove much better approximation guarantees. So in our works, now we analyze this algorithm and show that essentially, whenever the sequential greedy algorithm achieves a good approximation, then this distributed greedy algorithm actually achieves an approximation guarantee that is no worse than a factor of 2. Okay? So in the next few minutes, I'll try to tell you a little bit about how we do this analysis. This actually turns out to be quite simple in general. Any questions so far?
So do you have
Yes.
the number of machines has to be small for this, right?
The number of machines can be anything, so it's independent of the number of machines.
But k times the number of machines, number of sets should fit on one machine.
Right, so if we're working in a MapReduce setting, yes, then we have space constraints.
K is small.
Let's say that k is small. Okay, all right. Okay, so we get an enormous advantage from using randomization in the initial partitioning step. So what is the intuition for this? Roughly, the intuition is that, so let's think about a very good scenario where the elements of opt of the optimal solution are actually selected in the first round with high probability. Okay, so this seems to be the easy case, and indeed it is, because then we expect that most of the optimal solution will end up on the last machine. So when we run greedy, then we'll recover a very good solution just on the last machine itself. And at the other extreme, if the elements of opt are selected in the first round with very low probability, then that also seems to be somewhat of a good case, because there was a reason why greedy did not choose these elements when it was presented with a random sample. So the intuition here is that the optimal solution should not be very different from a typical solution. So then we would expect that maybe one of the solutions found on one of the machines in the first round is good. Okay? And this turns out to be the right intuition, and I'll tell you a little bit of how to formalize it. So the way we formalize this and analyze this actually it requires us to sort of notice a very nice property that greedy-like algorithms have. So the greedy algorithm has it, but also several others. Which is the following, which is rather intuitive. So imagine that we have a set S of elements. And imagine that we run the greedy algorithm on the set S together with another element X. And we do not select, and we end up not selecting X. So greedy passes on X. And the same thing happens when we run greedy on S union Y. So that means that X and Y were not very good. So elements in S were better. So if we have both an X and Y together with all of these elements in S, then greedy will not pick either X or Y. So on input S union XY, greedy does not select X or Y. So now that Y is there, it should not make X much more favorable. It still should be beaten by elements of S. Okay, so this is a property that the greedy algorithm has and other algorithms have. And we'll exploit this in the analysis. And also we'll work with some fractional vectors. So the second thing that we use is the Lavash extension of a submodular function. So you don't actually need to know the definition of this extension. So all you need to know is that it's convex, and it agrees with the function on integral vectors. So it's just an extension of the function so that we can talk about the value of fractional vectors. Okay? Okay, so now let me give you a very brief sketch of the analysis. So let's consider a random sample of the ground set. So each of the machines receives a 1/m sample, meaning that each element is there with probability 1/m, independently of all of the other elements. So now the key insight to formalize the previous intuition is to define the following very natural probabilities for elements of opt. So I'll let P be the probability over a random sample X that the element E is selected by greedy on top of X. So I have X and this element, and P is the probability that greedy will pick E. Okay? So since the distribution of on the input of each machine is precisely identical to the distribution of X, then it's very intuitive that if we look at the elements of opt that end up on the last machine, their distribution is given by these probabilities PE. So each element is, E appears there with probability exactly PE. Okay? So the expected value of opt in the last machine or in the final round is the Lavash extension on this vector P of probabilities. Okay? And on the other hand, all of the elements that we rejected, their expected value is the Lavash extensions of 1 minus P. So it's the complements, because they rejected probability 1 minus P. Okay? Okay. So how do we leverage that? So we can leverage the first observation in the obvious ways. So if we, so there's some subset of opt that ends up on the last machine, and we'll get enough approximation of that. So in expectation, this will give us a solution on the last machine that is about alpha times f hat of P. Okay? So that's the easy part. The most interesting part is what happens when these probabilities of P are low, so we are not getting very much out of this last machine. Then we want to say that whatever greedy picked in the first round in just one of the machines, let's say the first one, is already pretty good. Okay? And that is indeed the case. So we can show that if you just look at the solution on just one machine, let's say the first one, the expected value of that solution is proportional to alpha times f hat of 1 minus P. And the reason for this is that at every point, the greedy algorithm rejected elements of opt with that probability. And these are individual probabilities, but we have the greedy property. So that tells us that if a bunch of elements are rejected individually, they'll be rejected together. Okay? So we also get a good solution from the first machine. So if we put these two together and use the convexity of the Lavash extension, then we get an alpha over 2 approximation. Okay? And really, that's the analysis. And of course, I shoved many details under the rug, but really, this is all. Okay? Okay, so what did we use for the proof? So we used that the function is submodular and monotone. And we also used the fact that the constraint is hereditary. And perhaps the key property that we used was this greedy property, that elements that are rejected individually get rejected together. So that means that this is a fairly general proof. So we get constant factor approximations whenever greedy gets a constant factor approximation in the sequential setting. So this very simple randomized algorithm allows us to make the greedy algorithm parallel, which is perhaps surprising. Okay, so throughout the talk, I assume monotonicity for simplicity. One can extend this to non-monotone functions. So the algorithm, yes?
Are there high probability bounds?
No, it's just expectation, but you can always repeat this in parallel to get a high probability. Any Okay. So we can also handle non-monotone functions. And so the greedy algorithm doesn't work for non-monotone functions, but we can still use it in the first round. So in the first round, we'll run the greedy algorithm on each of the machines and get the greedy solutions. And once we put these together in the second round, we'll just use some algorithm for non-monotone maximization. And if we do this, we still get constant factor approximations. And we also lose 1 minus 1 over m. But besides that, it's exactly the same. Okay. Okay. So let me briefly mention some experiments. So we did several experiments to see how this randomization impacts the solution. So the previous work, the Mizar Suleiman et al. Paper, did extensive experiments with a cardinality constraint because that was the setting that they were interested in. And what they observed there is that this distributed algorithm does very well. So in particular for data sets for which they could run the greedy algorithm sequentially, this was actually very close to the sequential solution. So we also run some large-scale experiments. So we did 1 million tiny images with 100 machines. And indeed, it's sort of for a cardinality constraint, but this is the tiny images. So we want to pick k images. And indeed, these two are pretty close. So the dotted curve is the results that we get if we partition the data into blocks according to whatever ordering the input had. And the blue line is what we get if we do random partitioning. And in this case, they're pretty close, but at least we're not doing any worse. But there are some settings where we can actually get a significant benefit or noticeable benefit from the randomized partitioning. And it was this multi-mode sensor coverage problem that I mentioned. So if you have this kind of instances that I mentioned where we want to pick sensors modes for each of the sensors, the input now is the collection of ellipses. So we can distribute the ellipses in a rather natural order, where ellipses of the same sensor end up on the same machine. And if we do that, we get these black dotted curves. As you can see, this doesn't seem to be a very good allocation strategy. So the greedy algorithm is not doing as well. So whereas if we actually randomly distributed and spread out the ellipses of the sensors on different machines, this seems to work much better. Okay, so this is all I wanted to say. So let me conclude. So perhaps a very nice question here is whether we can go beyond this work. And there's several ways to do this. So one is to relax this greedy property that we use. So this is fairly general, but we are crucially relying on this greedy property. So we might want to run non-greedy algorithms on each of the machines. Can we actually do this? So another question is whether we could save on some space and running time on the final machine. So the final machine gets k times m elements, and this could be large. So can we reduce that? And there's always the question of whether we can do better approximation guarantees. So Vahab and Murtaza have some lower bounds in some settings, which are very interesting, but there still seems to be some room for improvement. So related to that, we have some follow-up work where we were able to get better approximation guarantees in more rounds. So for example, we can get the nearly optimal 1 minus 1 over e minus epsilon in 1 over epsilon rounds. So that work is on the archive if you want to take a look. Okay, so this is all I want to say. Thank you.